Good morning. This is Professor Grenfell coming to you once again for Math 12 Statistics at RCC. All right. This is 10.1 or 10-1 again. This is the chapter that will never die, apparently. Just kidding. It's not all that bad. So in this last example, hopefully this is going to finish off chapter 10, section 1. We're going to be testing rho. Remember, this one is rho, Greek letter. This is the population correlation coefficient. We're going to test that using table I. So this is in addition to our traditional method for doing a hypothesis test for rho, or the p-value method. We could do that, but remember, whenever we have to find a p-value and it's for a t-distribution or a chi-squared distribution, remember, there's not a real great accurate way of calculating that. We can just get a range of the values where that is between. Nicely enough, there is a third way, and that's what we're going to be looking at today. We're going to be testing rho using table I. Now, the nice thing about this is we essentially can skip step 3 in the traditional hypothesis test method. So we'll do step 1. We'll state the hypothesis. Number 2, we'll find the critical region. And this is going to be coming from table I itself. Now, since table I gives us the critical values for the PPMC, remember the Pearson product moment correlation coefficient, those are the values for R itself. And so this step 3 that we usually do, where we take our test value or sample value, that is, and we convert that into a standardized score, either a z-score or a t-score or a chi-squared value or an f value, and then we see where that is within the critical region. Here, our critical region is for the R value that we already have, so there's no extra calculation to do. Step 4 is still the same, make the decision. And then, of course, step 5, summarize the results. And remember that you're not going to say anything silly like rho equals 0, rho does not equal 0. We're not going to talk about rho. You're going to say it in words. You're going to say there is significant correlation between these two variables. There is a significant relationship between whatever it is that X represents and whatever it is that Y represents. Or you can say there's not a significant correlation between these, not a significant relationship. So that's how we would conclude the summary. All right, so let's apply this real fast. So we're going to proceed with example 10-8, found on page 559 of your text. And I have just gone ahead and copied down the information that we had there. So using table I, test the significance at alpha equals 0.01 of the correlation coefficient R equals 0.442 that we obtained in example 10-6. In example 10-3, we first constructed a scatter plot for the data. We observed that there appeared to be some linear relation between the X and the Y for this data. And then in example 10-6, the next thing that we would do, if we noticed that our scatter plot looked like it was kind of following a straight line path, is we'll go ahead and calculate R. We'll calculate the correlation coefficient. And then, continuing onward, we're going to do essentially this type of thing right now, either approaching it the way that we did in the previous example, 10-7, doing a traditional hypothesis test to test the significance of this correlation coefficient. Or here's an alternative style of doing it. We can use table I. Step 1, we'll state the hypotheses. Rho equals 0, that's the null hypothesis. Rho is not equal to 0, that's the alternative hypothesis. Whenever we are going to use table I, the critical values for R itself, we always are going to be doing a two-tailed test. So make sure your alternative hypothesis is always not equals, not one of the single-tailed options. In step 2, we got to find the critical region. So we'll be looking on page 788, or that's the 20th page from the appendices. We're using df equals 8. So we're looking in table I. Just make sure we're doing that. df equals 8 because here the data, we had a sample size of 10. 10 minus 2. Remember here, it's n minus 2 for the degrees of freedom. So that gives us 8. Alpha equals 0.01. And all of this, well, basically, we're just looking in a row and one column. Yeah, one row for the degrees of freedom, one column for alpha. And the value that we get is 0.765. So that value was pretty easy to find. Now, what is that? What do we do with that? Well, okay, so here it is on this side. This is positive 0.765. I'll put a little plus in front of it. And then on the opposite side of 0, we have negative 0.765. Since this is a two-tailed test, we have two rejection zones over here. This is a rejection, right? And over here in this region, we would reject the null hypothesis. Okay, and here's 0 in the middle. So essentially, it's kind of like this. If our R value, if our correlation coefficient is anywhere in this middle region, we're going to say, well, that's close enough to 0 that the population correlation coefficient, or the true notion of whether there is correlation between these values, you would say that is insignificant. If it is over here in the rejection region, here or here, we would say that is a significant linear correlation. So basically, we don't have to look at the distribution and the area underneath the curve. All this table of values gives us are these cutoff values from, whether we're over here and we're not in the rejection region, or whether we're in one of these value ranges and we're in the rejection region. So step 3 is we're just going to look at our value. Well, like I said, we don't even do step 3 because here's our value. R is equal to 0.442. There's nothing to do. We just find where this is. It is right here. It's not within the rejection region, so we fail to reject H subscript 0. And so we'll do step 5 the same way we always do. If we do not reject H subscript 0, we'll say there isn't enough evidence to say and whatever it says in H subscript 1. Okay? So we didn't find evidence to suggest the alternative hypothesis. Don't say that we accept the null hypothesis, though. We just didn't find evidence that proves the alternative. But that doesn't prove the null hypothesis. Can't. So we say, yeah, there is not enough evidence to say that there is a significant relationship between the number of teachers in the district and the number of pupils per teacher. So that was what, well, originally 10-3 and then secondarily 10-6 was talking about. Notice, we did not prove the null hypothesis. We did not say there is absolutely no relationship between the number of teachers and the pupils per teacher. We didn't say that. We didn't say H subscript 0 is absolutely true. We just simply said we didn't find evidence to suggest that it's not true, and we're just going to stop right there. We're going to only address the one lacking ramification of that, which is that we did not get the alternative hypothesis. We did not obtain the result that we were looking for. And I was going to close the video there, but I wanted to just quickly do a real brief summary, since this is finally now the end of chapter 10, section 1. So here's the scenario. We have paired data, and our primary question, is there a relationship between these two variables? The first thing to do is just a little bit of exploratory data analysis. That's a fancy way of saying we're gonna look at the data, and we're gonna give ourselves a visual graph to take a look at. We're gonna construct a scatter plot for the data. Just by looking at it, we should be able to tell, okay, we've got to be careful. We are not gonna automatically be able to tell whether there is a strong linear relationship between the X and the Y. We don't get that for free, but if there is no relationship, we will know automatically, because our scatter plot will be scattered all over the place and will not look like it's following along a straight line. So our scatter plot will at least tell us if we have to continue, right? Sometimes if there's no relation that is apparent from our scatter plot, then we just stop and we don't even proceed further. If it looks from our graph like the data points are all kind of trending together in a straight line fashion, either sloping upward, so there would be positive linear correlation, or sloping downward as you move along to the right, that would be negative linear correlation. If it looks like there possibly is correlation, then we're going to go ahead and do our calculation, right? So after we do step 1, if we don't see anything, then we get to stop there, right? Moving on, if we do see looks like a trend, a relationship between the X and Y value, then we'll go ahead and calculate R. And so what we will do after we have calculated it is we will test its significance. And now the nice thing about this is we actually have 3 ways of doing this. We have our traditional method, which we saw an example of. We have the p-value method, which we've done the p-value method using the t-distribution for numerous times. So that is something that we can do. And then lastly, kind of the nicest case scenario, you can do this as long as it doesn't instruct you otherwise. You can use table I to get the cutoff boundary values, the critical values for R itself, rather than having to take that R and convert it into a t-score. We'll just test that R itself as the test statistic using, of course, the table of critical values for R. All right, so that is finishing chapter 10, section 1. We'll move on to regression, coming up with the regression line equation in the next section. Stay tuned.